Let us look at convolution and convolution definition first. So what is convolution? How it is defined? Let us say that we have two functions f1 of t and f2 of t. Then f of t will be integral of minus infinity plus infinity f1 of tau multiplied by f2 of t minus tau d tau. That means one function is existing at tau, whereas other function is shifted by t minus tau. So when you take an integral of this is defined as convolution, indicated by the star here. That is, this is equal to f1 of t convolved with f2 of t. The star indicates it is a convolution. Therefore, f of t is equal to f1 of t convolved with f2 of t. Okay. We also use a star in some cases, but this also can be used, this also can be used. This indicates that two functions f1 of t and f2 of t are convolved in this. Let us see some properties of convolution. The first property is f1 of t convolved with f2 is equal to f2 of t convolved with f1 of t. Let us see a small example here. As you see here, we have a system which is an LTI system having a response of h of t, and input of the function system is f of t. Then the output will be the convolution of f of t and h of t. So if you see here, if I make the input as h of t and the system is having a function f of t, then the output will be h of t convolved with f of t. Let us see this. Let us take two functions. Let us say f1 of t is convolved with f2 of t. This will be same as f2 of t convolved with f1 of t. Okay, let us take a system. Okay, this is the input. Okay, and this is the output. So let us say the input is f of t, and let us take the output as y of t. Then if the system has a response of h of t, then y of t will be equal to f of t convolved with h of t. Okay. So when I give an input, the output will depend on the system's response and the input given. So system will respond to a certain input in a certain way, that is given by the function h of t here. So the output will be the convolution of the input signal and h of t, which is system. Okay. So now what I will do is, let us take another system here. Here let us say my input to the system is h of t, and let f of t be the system response. Then the output y of t will be equal to h of t convolved with f of t. Okay. So this is how a system responds. So we can say that the convolution of f1 of t f2 of t will be equal to f2 of t convolved with f1 of t. As you see here, both are same now. Let us see another property of convolution. Here if you see f1 of t convolved with f2 of t, the whole thing is convolved with f3 of t, then that will be equal to f2 of t f3 of t convolved, and the whole convolved with the f1 of t. So let us see this. Now we have, let us say I have three systems, f1 of t, f2 of t and f3 of t. These are three functions available. Three functions f1 of t, f2 of t and f3 of t. Okay, these three functions f1 of t, f2 of t, f3 of t. Let us see, let us say that I have convolved, first the convolution of these two is happening, f3 of t. Okay, the result is convolved with f1 of t. The convolution result of this is again convolved with f1 of t. This will be equal to, we can write this as f1 of t convolved with f2 of t, then the whole thing will be equal to convolution of f3 of t also. So this is the convolution. So it means I can convolve any function, and the function, the whole result of that convolution can be convolved with another function, will be similar to different functions being convolved together and the whole being again convolved with other functions. So this is the another property of convolution. Let us see another property of convolution. Here you see a function f of t is convolved with a delta function. Here a function f of t is convolved with a delta function. The result will be the function itself. So if you see here, diagrammatically, pictorially we have represented f of t when convolved with delta of t will result in the same function. So, what will happen if the function is shifted? Let us say the delta function is shifted by a factor t, then the function resulting function also will be shifted by a factor f of t minus t. Let us see this. Let us take a function f of t. Now, this is convolved with a function delta of t. The result will be f of t itself. That means, if you say, let us say this is a function f of t like this, okay, then again I have a function, this is delta of t. Okay. So, when I convolve this, the result will be f of t only. Okay. Now, let us say my delta of function, this is shifted by a factor of t. Now, this function is existing at, let us say a factor t, that is, this is delta of t minus t. When I convolve this, the result will be f of t minus tau. So, this is another important property of convolution. Let us see another property. If you see here f of t function here, if you see when this is passing through a system which is having a function which is equal to delta of t minus t, the output will be f of t minus t. In other words, the function is now shifted from earlier value of t is equal to 0 to another value, that is t is equal to capital T. So, this is called as an ideal delay or a copier. So, if you see this, a function, let us say, is existing at 0, this is 0 now. So, when this is passing through a function which is delta t minus t, when I convolve this, when this is convolved with delta of t minus t, I will get an output. The function now is at 0, let us say some function. Now, this function at 0, when it is convolved with the delta t minus t function, what happens is the whole function is shifted to another value, let us say this. So, if you look at this, there is a delay between these two, that is called as a, that is equal to t at which where the delta function exists. That means, now if I have such a convolution in our communication or any other system, if I want to delay a certain function, then we can pass this through a delta t minus t function, then that function will be delayed by a factor which is equal to t. So, this I can introduce delays into my system by taking such property of convolution. Now, let us look at the time domain convolution and frequency domain convolution. Here, if you see this, if two functions in time domain are convolved with each other, then the Fourier transform of that, that is, in frequency domain, there will be a simply multiplication. So, if you remember earlier we have done convolution time domain is integral minus into plus infinity f1 of tau, f2 of t minus tau d tau. So, that is a very big integral, that will take some time. So, what we can do is best convert the frequency time domain function into a frequency domain function, that is, convert a time domain function into a frequency domain. That means, when I apply a Fourier transform, then what happens is when two functions are convolved in time domain, the result will be multiplication in the frequency domain. So, all those integrations which we do earlier is removed, and now what we have is a simple multiplication in frequency domain. For that, we have to convert individually f1 of t, f2 of t, and then resulting frequency domain function will be a product when it is convolved in time domain. So, you see here, as we are seeing, looking at the same system, the impulse response of a LTI system is h of t, and the output is convolution of f of t and h of t. So, next, if I convert this, that means I am making my input a frequency domain function, that is f of j omega. Then the response of the system is h of j omega, then the output will be simply multiplication of the input and the system response, that is, the output will be f of j omega and h of j omega. So, when I apply Fourier transform properties, you can actually simplify the whole system, which will be a product of two functions rather than convolution of two functions. The same thing we are looking at, we have two systems here, H1, H2, and another system is added, H3. So, the overall output will be simply multiplication of all this. So, convolution from two functions, if it is going to three functions, it will be very difficult for us. So, when I convert into a frequency domain, it will be simply product of all the functions in frequency domain. That is what we see here. Let us look at one important property of convolution. We have a function which is given there, as shown. It is a certain function. It is being passed through a system which has or which exists only between minus omega p to plus omega p. Okay, as you see here, both are in frequency domain. So, the frequency of existence of the system response is from minus omega p to plus omega p. Okay. When this function is passed through it, what will happen? I will get an output which exists only for that duration of time for which the system response is there. Okay. So, this is called as ideal low pass filter. Okay. That means I am selecting only certain frequencies whose band of frequencies is existing from minus omega to plus omega. Let us see this. Okay. As shown there, I will try to replicate the same. Let us say you have a function like this. Okay. Let us say this is f of omega. This is passed through a system. Okay. Here the system is response is like this. It is existing from, let us say, a certain frequency omega p to plus omega p. So, when this is passing through this is also frequency, isn't it? This is also frequency domain here. So, when this passes through this, the output will be that part which actually falls in the same band. So, I will get a system response something like this here. Let us take only the top here. Okay. Let us say this is from minus omega p to plus omega p. Okay. That means we are doing what is called as an action called as a filtering. So, what is the filter that is happening here? We are selecting certain frequencies only from the input. So, that certain frequencies are what? Those frequencies which lie in the band of frequencies which are given in the system. That means only that part of the signal will come out which actually falls into this band. So, this is called as a filtering. Now, why we call this ideal? Because it is called ideal because the same shape is being retained. In fact, in a practical system, the shape there will be some distortion. So, we are calling it as ideal filter. So, this is coming, passing through this, getting filtered. The other components, like these are the components which are filtered out. Okay, and I am only getting those frequencies. So, these components are considered to be high frequency components. So, we call this as a low pass filter. Okay. This is a low pass filter and ideal low pass filter because of the fact that the shape is not distorted. So, this is an ideal low pass filter. Let us see another system. We have seen a low pass filter. Let us see a high pass filter here. If you look at this, the system response, you should concentrate on h of j omega here because that is what is changed from the earlier slide to this slide. So, earlier system, the function was existing between minus omega p to plus omega p. Now, if you look at this particular figure, now the function is existing beyond. Earlier it was from omega p to plus omega p. Now, the function is existing beyond this and beyond this. So, now when this is the filter, what will happen? Earlier this component has been eliminated. Now, they will appear in the output of the system because now here this is removed. Earlier what we have done, earlier low pass filtering, we have removed the high frequency components, and now what we will do is this particular function will eliminate the low pass, that means the low frequency components, but it will pass high frequency components. So, what I will get in the output? The output I will get something like this here and here. So, see, there is nothing in between here, there is nothing in between. So, this is called as a high pass filter. Okay, so, this is high pass filter and the output is this. So, this is how convolution can be used in filtering. Let us look at Parsifal's theorem. It is also called as energy preserving theorem, is also called as energy preserving theorem. So, what does it say? It states that an integral of minus infinity to plus infinity mod of f of t whole square dt will be equal to 1 by 2 pi integral minus infinity to plus infinity f of j omega whole square d omega. That means you can write it here. So, that is what the energy says minus infinity plus of infinity mod of f of t whole square dt will be equal to 1 by 2 pi integral minus infinity to plus infinity f of j omega whole square df. So, this is the Parsifal's energy theorem, also called as energy preserving theorem. So, you are squaring a mod of a function in time domain. Then if same thing happens in the frequency domain also, here also you have to square the mod of the frequency components, but the only difference is because we are taking omega here, it will be divided by 1 by 2 pi. So, that is a difference. So, this is how you have to find out the energy preserving using this formula. Let us do some examples now. The first example, let us take a pulse like this. Okay, let us call this pulse as g of t, where we are supposed to calculate the Fourier transform of a given function. So, function is given like this. For this, we have to calculate what is the Fourier transform. So, before actually starting, let us write down what is the formula which we have already seen. So, because this is given as g of t, let us say g of t is having a Fourier transform which is equal to g of f. So, g of f from our earlier knowledge is given by this formula minus infinity plus infinity g of t e to the power of minus j2 pi f t dt. Okay? We will make use of this formula. Or also, if you see this is a rectangular function which is centered around 0. So, we represent this as a rectangular function. Okay? What is the width of this function? The width of this function is t, whereas the amplitude is a. Okay? So, for a rectangular unit function is represented like this. Okay? So, if you see here the width is same as is given here, whereas amplitude, unit amplitude, earlier it is 1 here, now it will become a for us because this is the amplitude of a given function. So, g of t for us is given like this, g of t is equal to a rectangle t by t. Now, let us solve this problem by writing down what is g of f. Let us write the formula again. This will enable us to remember this permanently. Minus plus infinity g of t e to the power of minus j2 pi f t dt. Okay. What are the limits for us now? Our function is existing from minus t by 2 to plus t by 2. So, this will be minus t by 2 and this will be plus t by 2. So, what is the function here? A. It is existing, isn't it? So, let us also write here what are the limits of this, isn't it? So, what are the values? So, here if you look at this, g of t is taking two values. What are those two values? From minus t by 2 to plus t by 2, its value is a, and beyond t by 2, its value is 0, and below this minus t by 2, its value is 0. So, what are the two values it is taking? G of t is a for t less than t by 2 to minus t by 2, and 0 for t greater than t by 2. That means, our integration limits are only from minus t by t by 2, where its value that is being taken is a. So, we will put it here. Okay. Now, what is the formula we have to put here? It is minus j 2 pi f t dt. Okay. A is a constant. So, bring it out, a minus t by 2 to plus t by 2 e to the power of minus j 2 pi f t dt. So, the integration of that will be a by minus j 2 pi f e to the power of minus j 2 pi f t minus t by 2 to plus t by 2. So, let us write this here. So, how much this will be equal to? This will be equal to minus a by j 2 pi f. Okay. So, how much is this will be? This will be e to the power of minus j 2 pi f into t by 2 minus e to the power of minus j 2 pi f into minus t by 2 after substituting. So, this will be equal to a by minus j 2 pi f. Okay, this will be a to the power of minus j pi f t minus j pi f t. We know that sine can be expressed in terms of exponential functions. So, sine 2 pi f will be equal to how much? Sine 2 pi f t can be written as exponential of j 2 pi f t minus exponential of minus j 2 pi f t by 2j. So, this is similar here. So, what we will do is we will take j inside and then we will take the minus inside. So, this will become a by pi f here, and this will be a to the power of j pi f t minus e to the power of minus j pi f t by 2j. So, this is equal to a by pi f sin pi f t. Okay. Now, this I can write like this. This is equal to a of sin pi f t. Here t is not there in the denominators, but I will add t here and then I will put t here. So, I have divided and multiplied by. Now, why are we doing this? Because we want this to be in the form of a sinc function. Now, this is a sinc function. So, this will be equal to a t sinc function of f t. So, this is a t sinc f t. Now, if you look at this, I have a rectangular function in time domain and this is my Fourier transform of it, which is a sinc function. Now, let us draw the plots for these two. Now, a rectangle t by t is having a Fourier transform which is a t sinc f t. So, this is a sinc function. Now, sinc function we already know what is the wave shape. So, let us draw it in the form of a waveform here. Now, the sinc function, let us take this is the amplitude of this. So, what will be the first amplitude? Sinc function first amplitude will be equal to a, which is this. Now, the first crossover will occur at what place? T by 2. That means, the first crossovers will happen at plus or minus t by 2. Now, if I draw the frequency spectrum of this, shape looks like this, whereas the maximum amplitude is a. The first crossover happens at plus or minus 1 by t. So, 1 by t, the first crossover happens. The second one will happen at 2 by t, the third one at 3 by t. So, similarly, here also this is minus 2 by t and this is minus 3 by t. So, here a rectangular function in time domain is transferred to a sinc function like this, whose amplitude spectrum is this. The phase spectrum will be plus or minus 180 degrees. So, this is the amplitude spectrum. Let us analyze this a little. Now, if the value of t is decreased, what is happening? The frequency components are moving apart. If I increase the value of t, these functions are moving towards the origin, that is 0. In other words, if there is an increase here, there is a decrease. If there is a decrease here, there is an increase. That means, there seems to be an inverse relationship between the time domain and the frequency domain. So, one important point where you have to understand here is, if the pulse is very narrow, let us say that I have a very narrow pulse like this. That means what? The t is very small here. When you have a very narrow pulse like this, when I get a frequency components of this, the frequency components will be wide. That means, I will have frequency components which are existing very widely. So, a small time domain function will result in a wide frequency domain function. So, if I have a function which is width is very big, then what happens is the number of frequency components will be reduced. So, this helps us in analysis with this particular property. Let us see a second example. Okay. So, this is the function which is given to us. This is an exponential function u of t. Now, we have to calculate the Fourier transform for this. So, let us say this is again g of t. So, I have to calculate what is g of f. So, g of t will have a Fourier transform that is equal to g of f, and g of f is given by the formula minus infinity to plus infinity g of t e to the power of minus j2 pi f t dt. So, this is the formula which we already know. Now, let us calculate for this. What is the function for us? This is the function, exponential function. So, g of f, okay, the limits are minus infinity to plus infinity g of t e to the power of minus j2 pi f t dt. So, this will be equal to, the function is existing from 0 to infinity because u of t is there. So, this is 0, this is infinity. What is the function here? G of t, e to the power of minus t and e to the power of minus j2 pi f t dt. So, this I can take minus t common. So, this will be plus 0 to infinity e to the power of minus of 1 plus j2 pi f into t dt. Okay, we have taken t common here. So, what is the integral here? That will be equal to minus 1 by 1 plus j2 pi f exponential of minus 1 plus j2 pi f t, okay, from 0 to infinity. So, this will be equal to 1 by 1 plus j2 pi f. So, this is the Fourier transform of an exponential function. So, this is our g of f. Okay. That means, I will just write it here, e to the power of minus t will have a Fourier transform which is equal to 1 by 1 plus j2 pi f. Okay, let us take a third example and see an extension of the earlier example. Now, let us take a function again g of t. The earlier example was exponential decay function. Let us say it is an exponential rising function. So, this is e to the power of t u of minus t. Okay. So, what will be the case here? So, this will be from minus infinity to 0. For us, what is t? E to the power of t e to the power of minus j2 pi f t dt. So, if I do all this and then I do the integration, then I will get an answer which is equal to 1 by 1 minus j2 pi f. So, this will be my g of f. So, if I look at this problem and the earlier problem, e to the power of minus t is having a Fourier transform which is 1 by 1 plus j2 pi f, and e to the power of t is having a Fourier transform 1 minus j2 pi f. That means, I can put these two together and probably I can write e to the power of minus plus of t will have a Fourier transform which is 1 by 1 plus or minus j2 pi f. Okay. So, that means, if it is e to the power of minus t, then this will be 1 by 1 plus j2 pi f, and if it is e to the power of plus t, it will be 1 by 1 minus j2 pi f. So, these two formulas you should remember. So, this will give you what is the Fourier transform of exponentially decay function and what is the Fourier transform for an exponentially rising function. Okay. So, this is the third example. So, this is example 4. Okay. Let us say the function given is this is the function. Okay, let us draw how does it look like. So, g of t will be okay, this is the function, this is our g of t. So, this is where we have to calculate the Fourier transforms. So, as usual, let us say the Fourier transform of g of t is g of f, and g of f is given by this formula. Okay. These two are known to us. Now, we have seen the Fourier transform properties and we have to identify which property is going to help us here. Okay. The first property of Fourier transform says a linearity or a superposition property. Let us use that property here and find out what will be the overall response or overall Fourier transform of a given function. Because if you see here, we have seen third example and second example. So, this is an exponential decay function, we have calculated the Fourier transform for this. This is an exponential rising function which you have calculated the Fourier transform for this. So, if I use a linearity or superposition property, the Fourier transform of this plus the Fourier transform of this will give me the overall Fourier transform. So, let us get that here. So, let us use linearity property Okay. So, that means g of f will be equal to g1 of f plus g2 of f. Okay. Let us call this as g1 of t and this as g2 of t. Okay. So, what is the response of this? This is e to the power of minus t. So, this will be 1 by 1 plus j2 pi f plus this is e to the power of plus t. So, this will be 1 by 1 minus j2 pi f. Okay, let us take LCM of this. So, this will be equal to 1 by j2 pi f plus 1 plus j2 pi f by 1 plus j2 pi f into 1 minus j2 pi f. Okay. So, this will be equal to 2 by 1 plus 2 pi f whole square. So, this is our GF. Okay. We have applied the linearity property here, otherwise what is that you have to do? You have to again calculate from minus infinity to plus infinity, integration, all those things, but because we know the linearity property, we have already derived a result earlier which you are trying to make use here. So, what I suggest to you is, because these type of questions are asked, lot of questions are, these type of questions are asked in objective type mainly. So, if you remember these formula, you can just directly apply them. So, our approach is towards that, where we will try to find out how the properties, various properties which you have studied are useful here. So, this will be a total overall response of a system which is a double sided exponential function like this. Let us see the fifth example. Okay. Given g of t is equal to e to the power of minus 8. Now, we have to calculate the Fourier transform of the signal. So, how does the signal look like? Because this is an exponential function, decay function, it is starting from here. Okay. So, this is the time and this is my g of t. Now, how to calculate? Now, let us see the two ways of doing this. One is, we know g of f is equal to that formula which you can integrate and get the answer. The second is, try to identify an appropriate Fourier transform property which will be useful for us here. So, the two ways. So, the best way is, the simplest is second one, where I will try to identify what are the properties which can be used here. Now, the problem which you have seen earlier, we spoke about e to the power of minus t. Now, we are speaking about a function which is multiplied by min a here. So, that is, it's an exponential function which is scaled by a factor a. So, we have to use time scaling property. So, what does time scaling property say? Okay, time scaling property says, it says that g of a t will have a Fourier transform which is equal to 1 by mod a g of f by a. Okay. Here you should remember one very important point here. When I am multiplying a function g of t, the time is multiplied by a, that is scaled by a factor. So, what is happening here is, here we are doing what is called as a compression. Okay, compression in what? Time domain. This is compression in time domain. So, what is the resulting frequency domain? If you see here, the frequency domain is getting divided by a. That is, this is expansion. Expansion in frequency domain. That is, when I compress a signal in time domain by a certain factor a, the resulting Fourier transform will have an expansion in frequency domain by the same factor a. That is, compression by what factor? A, and expansion by what factor? A. So, this is a very important property. When I compress in time domain, it will be expansion in frequency domain and vice versa. Okay. So, let us use this property here and find out what is the Fourier transform of the given signal. We know that e to the power of minus t is having a Fourier transform which is 1 by j2 pi f. So, e to the power of minus at will have a Fourier transform based on the time scaling property. Okay, I use time scaling property here. minus at will be 1 by a as is here, then 1 by 1 plus j2 pi into f by a. Okay. So, this will be equal to 1 by a to 1 by a plus j2 pi f by a. So, this get cancelled. So, I will have a Fourier transform which is 1 by a plus j2 pi f. So, this is the Fourier transform of e to the power of minus at. Okay. See, we have used two properties here, or two what we know, two facts. One fact is we have identified that this problem is related to time scaling property. The second is we have already calculated what is the Fourier transform e to the power of minus t. Those two things we have put it here, and then I got an answer which is a Fourier transform of e to the power of minus at 1 by a plus j2 pi f in just